All right, now here we are getting further into the gases chapter. We've just summed up some of the key points of Boyle's law, and we're on to another of the gas laws here in section 4. So Boyle's law related the concepts of volume and pressure. Now in 7.4 here, we're going to look at the impact of temperature on volume, or Charles' law. So we'll take a look and see how temperature and volume are related in a gas sample. So Charles' law states that the Kelvin temperature, notice that, very important, it must be Kelvin. Kelvin is the absolute temperature scale. So the Kelvin temperature of a gas is directly related to the volume of the gas. So if you remember Boyle's law, we had pressure and volume were inversely related. Here we have temperature and volume are directly related. Just like we held temperature and number of moles constant for Boyle's law, here in Charles' law we're holding pressure and number of moles constant. And then finally, as temperature of a gas increases, the molecules are moving faster and the volume also increases to maintain that constant pressure. So think back to kinetic molecular theory of gases from the first part of chapter 7 here, where we talked about properties of gases. And again, those gases are moving. The higher the temperature, the faster on average the gas particles are moving, and therefore if we're going to keep pressure constant, we'll have to expand the volume in order to maintain that constant pressure and constant number of moles. The form of the equation here, because it's a direct relationship, it's V1 over T1 equals V2 over T2. As a reminder, of course, Boyle's law was P1 times V1 equals P2 times V2 because they were inversely proportional. They were multiplied together. Here, because it's a direct relationship, they're divided, volume by temperature. So again, expanding on that theme of the temperature of the gas increasing, the molecules therefore moving faster on average, the volume must increase to maintain that constant pressure, and we see here at a lower temperature condition of 200 Kelvin, the gas would occupy a volume of 1 liter. As we increase that temperature now to 400 Kelvin, the piston we see expanding to increase the volume now to 2 liters because we doubled the absolute temperature. Therefore, we need to double the volume in order to keep pressure constant. That same average number of collisions against the walls, which is the pressure, remains constant if we double the volume when we double the temperature. As we did for Boyle's law, Charles' law, again, being a law in chemistry, it's going to probably have that succinct relationship that we talked about before, V1 over T1 equals V2 over T2. So let's work a problem together and see how we apply those steps we learned back in 7.3 to this section 4 of chapter 7. The problem here, a sample of neon gas has a volume of 3.1 liters and a temperature of 12 degrees Celsius. Find the new volume of the gas if the temperature rises to 32 degrees Celsius. Assume the pressure and amount of gas remain constant. So before we go to step 1, just a reminder, those Celsius temperatures, it looks here now that we've more than doubled the temperature from 12 to 32. If you've forgotten that we need to be in Kelvin. So when we go to our steps here in step 1, organize the data in a table of initial and final conditions and analyze the problem. Of course, we need to convert those temperatures. Whenever doing anything with gases, it's always the good first step to convert temperatures into Kelvin, because if you don't, if you forget that, then you know me, there's going to be an answer choice that is for the Celsius or Fahrenheit or whatever other temperature scale you might have used, and it's going to be a distractor, a wrong answer choice, because you know you need to use Kelvin. It's a good idea always to use Kelvin in chemistry, but in particular when we're dealing with gases. So here we have it, T1 equals the 12 degrees Celsius, but in order to convert it to Kelvin, we need to add 273 or 273.15 if you want to be very specific, in order to get here a 285 Kelvin. The V1 is 3.1 liters, T2 is 32 degrees Celsius, again converted into Kelvin by adding the 273 gives us 305 Kelvin, and then V2 is what we're actually looking for, and we know that as temperature increases, volume should also increase as a result of that direct relationship that is Charles' law. Moving on to step 2, we can rearrange the gas law equation to solve for the unknown quantity. So here we have V2 is what we're solving for. The way that we're going to isolate V2 is to multiply both sides by T2. Since originally V2 was being divided by T2, that will cause it to cancel on the right-hand side. And then as we flip the direction of our equation, we end up with V2 equals V1 times T2 over T1. And looking at that form of the equation, or the original form of the equation, we see temperature in the denominator. That's one of the main reasons we can't use the Celsius temperature scale or the Fahrenheit temperature scale or any temperature scale for that matter where you have a 0 value for temperature, because if you have a 0 in the denominator, any fraction divided by 0 is undefined, and therefore we can't use 0 degrees Celsius or 0 degrees Fahrenheit. We have to use our Kelvin scale, which really doesn't go down to 0 or doesn't officially go down there, although we've gotten to understand that we're a little off with the Kelvin temperature scale when we get very, very cold. And finally, here in step 3, we can substitute the values in, or at least the values that we solve for after converting into the Kelvin scale, and then solve the equation. So V2 equals V1, the 3.1 liters, times the 305 Kelvin, divided by that 285 Kelvin, and therefore we get a final value here of 3.3 liters. So if you looked at those Celsius temperatures and thought we more than doubled our volume, we certainly did not. We only increased the volume by a very small amount, because in terms of the absolute temperature scale, we only went up by a small amount. All right, so now that we've worked one together, here's a learning check to see how you do on your own. In this example, a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon? Again, holding pressure and number of moles constant. So please stop the video now, go ahead and solve the problem, and when you're done, start it back up and we'll see how you did. All right, I hope nobody was fooled by those temperature values, right? I have warned you already. Do not trust Celsius. It is the Kelvin scale only that we use in gas laws. So conditions: V1 equals 785 milliliters. T1 of 21 degrees Celsius converts into 294 Kelvin. V2 is what we're solving for, just like in the one we worked together. And now T2 is not 0 degrees Celsius. If you went that route and you ended up with a T2 in the denominator, then hopefully you saw that your calculator gave you an undefined result, because really you need to use 273 Kelvin. And of course, since we know that the temperature has decreased, we predict that the volume has also decreased due to that direct relationship. Okay, and following up with step 2, we rearrange the gas law to solve for the unknown quantity. Again, multiply both sides by T2, and then we can isolate V2. And once we substitute in the values, if you had done the 0, I forgot the 0 would end up in the numerator here, so you just end up with a 0, and then you multiply 785 by 0, and of course you can't have a 0 volume, so that should have clued you in, and hopefully you caught your mistake if you made that mistake, which is common, and when you correct for the correct Kelvin scale temperatures, you get 785 milliliters times 273 Kelvin over 285 Kelvin, and indeed that does cause a decrease in volume to 729 milliliters. So don't feel too badly if you did make the temperature mistake. It happens. Better to make it here than on the test. And if you didn't make it, good for you. Don't get too full of yourself, because we don't want you to make that on the test, definitely. So be careful with the temperatures, especially as the exam approaches. But hopefully, aside from that very common mistake, you've been able to follow what we've done here with Charles' law, and it's not much different than Boyle's law, just the equation's a little different form because of the direct relationship versus the inverse relationship. If you're having trouble with either law, please do reach out to me. Otherwise, we'll meet up again for the next section, which will deal with yet another law.